Throughout the years, camera gimbal systems mounted on drones or helicopters became an indispensable part of filming equipment, both for hobbyists and professionals. This is the reason we decided to model the dynamics of a camera gimbal system and its control.
To start modeling the system, it is of course important to clearly define the used frames of reference. They can all be seen in the figure at the right side of this slide. The black frame is the frame of reference of the Earth, which is standing still at all times. The blue frame moves with the drone, and the green one is the frame of reference of the camera itself. To describe mathematically the motion between the different frames of reference, rotation matrices are used, which are composed as can be seen on the slide. R phi represents the motion of the drone with respect to the Earth, and R theta the motion of the camera with respect to the drone. Multiplying both matrices results in the orientation of the camera with respect to the Earth. To know the angles alpha from this matrix, the formulas of the Euler angles are used. They are also given on the slide. When having a desired orientation, the needed value of theta can be calculated. This one is needed to steer the DC motors of the gimbal system. Now we'll explain how we got the dynamic system model. First, the angular velocity of the camera with respect to the Earth is written out as shown in the slide. Mu, x, y, and z are the velocity primitives of the rotations about the x, y, and z axis respectively. By filling in everything in the formula of omega CE, which stands for camera Earth, of the values of omega CE, x, y, and z can be obtained. The vector omega contains those three elements. The kinetic energy T can then be calculated using this vector together with the inertia matrix. The inertia matrix was obtained in SolidWorks using the model shown in the picture. With the kinetic energy, the equation of Euler-Lagrange can be applied for all three generalized coordinates, resulting in the set of equations given on the slide. Those equations are then solved to the second derivatives of theta 1, 2, and 3.
Springs and dampers are added in order to allow a smooth motion of the camera and to reduce the torque vibrations due to the DC motors. Small modification has to be made to the Euler-Lagrange equations obtained on the previous slide, due to the fact that the motor torques are no longer equal to the torques exerted on the camera, and the motor angles are also no longer equal to the camera angles. First of all, the right-hand side of these equations, the motor torque has to be replaced by the corresponding torques due to the springs and dampers, and three additional equations have to be added in order to relate the motor torques to the torques due to the springs and dampers. The motors were modeled using the standard DC motor equations, and an additional part was added to incorporate the torque ripple due to the brushes. The motor encoders are modeled as well, using a transfer function that incorporates the bandwidth, and white noise to model the encoder noise.
To test our model, we designed an algorithm that produces fake flight data. For starters, limits to the rotation around the x, y, and z axis were set into place. Every angle change, a new rotation matrix was drawn and applied to the coordinate system. This rotating coordinate system can be seen in the video below. In the end, the coordinate system will always return to its original position. The rotation sequence is x, y, z. A detailed description of the algorithm can be found in our report. The rotation matrices are saved and the pitch, yaw, and roll angles calculated and passed to a moving average filter. This is done to filter out the rough peaks. Then the simulation can be used by our model.
The PID control scheme assumes a decoupled system, which is not strictly the case. Nevertheless, the controller performs very well. The PID controllers are tuned using a genetic algorithm with multiple simulations of 80 generations, and the best PID gain values were selected. An example of such a simulation of 30 generations can be found on this slide.
Let's proceed with the adaptive model predictive control. As our system is highly nonlinear and has a continuously changing operating point, the standard MPC approach was not possible. For this reason, we worked with the adaptive MPC toolbox. The toolbox takes a changing state space model, A, B, C, and D, as an input, which a standard MPC couldn't do. The measured outputs, stated as Mo, the model output reference, stated as Ref, and a standard MPC controller, MPC1, are also seen on the input. This standard MPC is tuned on nominal conditions. These tuning parameters, weights, constraints, state estimation, control, and prediction horizon, are all inherited from the adaptive MPC, MPC1. The input rate and voltage is no real constraint, so weights of the input rates were determined to be 0.108, whereas the error on the output signals is of bigger importance and was fixed on 7.3. A more aggressive approach could lead to instability. It also becomes clear that the voltage doesn't risk to go beyond its allowed range. The prediction horizon is the amount of time steps into the future for which the future states are simulated. Increasing the prediction horizon results in improved performance, but this comes at the cost of increased computational effort. For this reason, a prediction horizon of about 15 samples was determined. Above 15, the performance does not significantly increase anymore. The same reasoning goes for the control horizon, which was fixed on 4. Finally, the state estimation rate was determined. Faster state estimation reduces the error.
If we check the performance of PID and MPC separately, we see that performance of both are similar. This can be seen from the error on the orientation angles. The MPC is computationally more expensive but takes into account the input constraints. Possible grounds to be explored are to apply a PID first and an MPC afterwards. This idea was also explored in computer control of industrial processes.